Welcome to the Internet of Things workshop by Design Your Careers. In this workshop, we're going to be covering various things ranging from how to use the Raspberry Pi to several simple demonstrations and projects involving sensors and all sorts of things that you can purchase online and do at home. So what are we?
Design Your Careers is a global platform that allows students to serve their career opportunities and have chances to advance their passions. Students can explore their unique knowledge, interests, and abilities.
So the workshop is actually presented by me and co-presented by my friend Rohan, and I'm currently studying computer science at UC Berkeley, and I plan to work in the computer science field. I have taught in the past CS classes at various libraries, and I've taught them at several enterprise locations as well. I've held many CS internships and hope to continue pursuing this domain in the future.
Hi, I'm Rohan. I'm a sophomore at Santa Clara High School. I'm interested in computer science, and I'm also taking computer science in my school. I hope to follow this path and hopefully pursue a career in the future involving computer science.
So what really is IoT? While the Internet of Things is quite a complex subject that most people don't really understand despite its buzz in the media sometimes, it simply comes down to facilitating a beneficial connection between various pieces of technology, hardware, software, and that it helps us in some way or form. In other words, any smart homes, locks, etc. facilitate this exact connection that help us guard our possessions or, deliver items to us faster in a more secure way. Nowadays, even shopping, delivery drones implement various elements of IoT, like, for example, the recently sensationalized Amazon drone, to more effectively transport goods that would otherwise take far longer and utilize many more resources. And this sort of cooperation between hardware and software breeds what really makes IoT so powerful. You may be wondering, how is IoT actually implemented in terms of the hardware and software elements, because it's a lot of theory until now. It usually comes down to the inner workings of the sensors and various actuators in combination with the software that controls the back end. From simple sound sensors that send alerts to your phone as parts of home security solutions to really complex smart home implementations, all IoT applications just involve cooperation between software and hardware. And nowadays, even cloud solutions are gaining popularity, what with the Amazon cloud and many other types of cloud services.
You may ask, what are the applications of IoT in the real world? Well, IoT is very versatile. It can be used in automation of buildings and homes, manufacturing. It can even range up to healthcare systems and medical in the modern era. Media and environmental monitoring also use IoT. The history of IoT, well, it's a very interesting topic. Since the 1970s, the idea of wanting to interconnect devices to accomplish something bigger and greater that is beneficial to our society and helps our daily lives. Kevin Ashton, however, was the first one to coin the term and create this revolutionary apparatus that allows for accessibility and creates opportunities to improve our world. It started with the Google Maps 360 view in 2010, where it entered the hype curve and shortly skyrocketed due to its versatility and usability.
The entire reason why the Internet of Things is such a revolutionary field in the modern day is due to its evolution past the realm of direct interaction with computers, or in other words, HCI, human-computer interaction. For decades and decades now, since even the 1940s, the only form of interaction with computers has been through physical contact, like through keyboards and mice, and otherwise relatively restricted remote access protocols like SFTP or FTP. By expanding the horizons for technological communication through the internet, IoT is probably at the frontier of automating and rendering jobs more efficient in the workplace now. But to a certain extent, this is also what makes it quite controversial. IoT is so efficient and so applicable in so many fields that it often pries away jobs from hardworking individuals and phases out jobs structurally in many industries. This moral debate is, up in the air and remains to be explored in the future, but it's something definitely to keep in mind.
When it first entered the Gartner hype curve, IoT was what we would call the innovation of trigger, where it joined other revolutionary technologies that hope to shape the future of computers. Right now, things such as edge analytics and digital ethics are starting up. At this point in time, IoT is towards the end of its peak of inflation, where it is extremely hyped and opened up many opportunities, ideas, gates to new technologies, and where many companies are investing time and money. It is among many other ideas with innovation, including machine learning and event stream processing. Soon it is going to fall into a trough where it will die out and slowly reach a plateau and try to regain some of its usability. According to this hype curve, because IoT is dark blue, it is predicted to reach its plateau in anywhere from 5 to 10 years.
Well, as I mentioned above, many applications of IoT are quite complex in nature, and that often prevents many passionate people about the field from exploring it. However, there are many instances of implementing IoT applications that are quite simple in nature that people just don't get to, and they provide a perfect computational exercise for those that are really interested in the field. Some basic implementations obviously include those with sensors and actuators, and in this workshop we'll actually talk about the sound, ultrasonic, and motion sensors. But in general, these sensors will communicate with various hardware and software elements to carry data through the internet and process on the fly. That's the world of the Internet of Things, and let's explore this further with the Raspberry Pi.
This is the first demonstration we're going to do with the Raspberry Pi 3B, and it's with a simple sound detector. And this simple sound detector has 4 pins, but we're only going to use 3 of them: power, ground, and analog output. So what you're going to do is connect 3 female-to-female jumper cables to the 3 pins, analog out, ground, and the 5-volt pin. And the power pin is going to go on the top left, and then the ground pin is going to go on the 3rd on the top row, and the analog output is going to go on the 6th pin on the bottom row. And once we're done with that, our hardware configuration is complete for our first demonstration. Let's jump into the software side.
Let's take a look at this Python implementation of sound detection one step at a time. So the first line is something that's reserved for Linux implementations of Python. It essentially just calls on the interpreter to analyze the file and run the program. The first couple of lines are quite important. The first of which is actually the Raspberry Pi module, which actually enables the whole program to work. This is the Raspberry Pi general purpose input output, and those are actually interfacing with the pins on the Raspberry Pi to transfer data between the Pi and the computer. This is obviously an element of IoT, and it's the underlying basis for our entire program. All the other modules are normal system modules like time, OS, and sys. Most of these are used for actions like exiting and all that sort of stuff. We'll take a look at the next 3 lines later on when we implement sending emails and all that sort of stuff from Python. But for now, we're just going to make a function called detect sound, which, as it says, detects the sound. It sets the channel, which is actually the pin number, the general purpose input output pin number on the Raspberry Pi. So if you have a Raspberry Pi 3B, it'll match up with the exact same pin that we are using currently in our video. We set the mode to BCM, and then we set up the pin number 17 as an input channel. We define a function then called callback, nested inside the detect sound function, and we point it to a channel, and that channel is obviously going to be channel number 17. And when we detect sound, it's going to return a Boolean value of true, and since this is analog output, it's either going to be true or false. When we get true, we just print sound is detected, and when we don't get any sound detected, we just return from this the nested function. To run the whole program, we add an event to the general purpose input-output stack that allows the Raspberry Pi to detect whether there has been any sound changes or not, and we just run this continuously by sleeping for 5 seconds at a time. And whenever sound is detected, it'll call that callback function and we'll get sound detected printed. And so that's essentially how the program works.
Alright, so now that we've written the program, we just need to launch it. And to do that, we're going to type /sound.py, and this is our Python file. And when we hit enter, we're just going to be greeted with a blank screen until we make a sound.
Many misunderstood tech buzzwords are going around, such as machine learning. However, these are all limited, as they are restricted to limited development environment, as with quantum computing and etc. The use cases are extremely restricted. However, on the other side of the usability spectrum, IoT is full of solutions and has a broad range of possibilities. And as such, IoT is the answer to many everyday problems, unlike other rising technological solutions.
So let's get to the Raspberry Pi and what it can really do. Well, simply put, the Raspberry Pi was invented as a sort of computer in the palm of your hand. It's the size of a credit card and has a lot of usability in terms of IoT, since it has a wide range of applications for sensors, and it can connect to the internet. It can connect and interface with the keyboard, mouse, through HDMI. And so the Raspberry Pi is essentially a one-man computing machine. Since we've already explored what the Raspberry Pi is and what it can do physically, let's talk about some of the applications, IoT or otherwise. One of the most famous IoT applications is obviously the home security systems, which combines a host of various sensors such as a sound sensor, ultrasonic sensor, and even the motion sensor to provide a secure feeling to your home. There's also the weather station reporter, which fetches data from the internet to report the weather. The Pi Radio, which streams FM and AM, and online photo booth and gaming streaming console are sort of add-ons which are just fun. But all of these have a commonality in that they all have a host of sensors that help bridge the gap between hardware and software. So how do we actually get started with Pi? Before you actually get into it, you need to decide which programming language you're going to start with. Most people start with Python because it has it's relatively lax syntax and it's quite easy to pick up for beginners. It also gets you oriented with the basics of Linux and the basics of coding in the terminal. And so if you really want to go deep and learn more languages, you have to install appropriate libraries, since other languages are probably not installed besides Python. And let's begin.
Well, what do you need for a Pi setup? Initially, you need the essentials such as a mouse, keyboard, monitor, internet connection, and USB power source.
And once you have all those set up, you simply just plug in your peripherals. That means your mouse, your keyboard, monitor cables. You'll need this for the first time setup, but after that you'll be able to SSH in right into your Raspberry Pi since it's a server. Your Raspberry Pi is going to boot, and you're going to get a set of different operating systems that you can install. I recommend Raspbian because it's quite simple to use and it's quite light. Once it runs through the installation process, it's quite easy. Just wait. It'll be about 20 to 30 minutes depending on the model of Raspberry Pi you bought. Once it loads, you simply log in with the username Pi, password Raspberry, and if you're greeted with the terminal, you just hit Start X and hit Enter, and you're right there. So before we delve into the programming side, let's actually take a look at what makes the Raspberry Pi so unique and powerful. First of all, it has quite a beefy CPU for something that size. It's 64-bit, 1.4 gigahertz, and it's got 1 gigabyte of LPDDR2 SD RAM. It's got obviously the GPIO pins that we need to interface with sensors. It's got Ethernet, and it's also got Wi-Fi, 2.4 gigahertz and 5 gigahertz. It's got a HDMI and display port, and 4 USB 2 ports just for keyboard, mouse, and all that sort of stuff. So the pinout specifications are what you you're going to need to know when you get to the sensor part of the IoT configuration. So you'll notice in the top left of the pinout specification it says 5 volts and 5 volts. So that's actually where the power is going to come from for the sensors. So with the power from those 2 pins, and obviously you're going to need a ground pin for all of the sensors, and a connection to GPIO, one of the GPIO pins, 14, 15, 18, 23, 24. There's many of them. You can connect to any one of them, and you have to configure the channel through which you're getting the input, and you have to configure the channel through which you're sending the output.
Well, why Pi? Pi is the answer because it has a low cost, supports plethora of sensors, high processing power, small and portable as it fits in your palm, a marketing strategy, interfaces with standard I/O, and great for beginners and experts due to its versatility.
And before we get to actually implementing these sensors, what really are sensors? And simply put, sensor is something that gathers data from physical stimulus. In fancy electrical engineering terms, it's a transducer that converts a physical stimulus into an electrical stimulus, and it has 2 separate categories, analog and discrete, or digital. We're mostly going to use analog, which is sort of, simply put, is a binary 0 and 1 kind of thing, where you usually measure whether it's a sound or not, there's motion or not. In some cases, when we're using the ultrasonic sensor, we're going to need a more complex setup as well. So which Pi should I get is the question a lot of people face when they're getting their first Raspberry Pi. And here are a bunch of revisions and models just to confuse you. So we have the BREV1, BREV1, BREV2, all these sorts of models. Which one is the best? Well, it really depends on the cost you want. Most of them are fairly inexpensive. Most of them come around $20 to $40. I would recommend go for the most expensive model just because it has a lot more computational capability. The 3B is quite good. The 3B Plus, which just came out, is also quite good. Anything you can afford is probably doable with regards to how much computational power you actually need.
If the Pi doesn't suit your needs, there are also many other alternatives that can help suit your preferences, such as the Orange Pi Prime or the Banana Pi M3. If you want something more like a microcontroller, you can use the Arduino. There are, of course, other alternatives that can help suit you.
Alright, welcome to the first main Raspberry Pi project. For this one, we're going to be adding on to our previous demonstration, and we're going to be adding a motion sensor. So this motion sensor has 3 pinouts, just like the last one. This one has VCC, which is power, out, which is going to be analog out, and it's going to have ground like always. So the power pin goes on the second on the top now. Second pin on the top. The ground pin goes on the 5th pin on the bottom. And the out pin, the analog out pin, is going to go on the 8th pin on the top, which is GPIO 23, general purpose input output pin number 23. And that's where we're going to read all our data from. And now that that's done, let's move on to the software part. That's it. Since our parts are quite low quality, we're going to have to simulate an environment in which home security is preserved first. So we've chosen a Tetley box, which is quite dark, and so there will be no motion. So this box, we're going to put the motion detector, and once we move the box or we move the sensor in the box, the motion detector is going to go off, and the sound detector will be outside because obviously can't detect sound while being inside the box. So that's our current setup, and so let's do that. Let's put the Raspberry Pi with the motion sensor inside the box and the sound detector outside the box. And now we're ready to launch our application.
So for our first project, for our first main project, we're going to talk about how to implement a simple home security system with sound and motion sensors. Now, as you may remember, a couple of slides ago, I talked about some of the applications with regards to IoT, as well as just random Raspberry Pi projects that you could make a home security system. And this is the most basic version of that, which incorporates sound detection and motion detection. So, you know, if there's a loud sound or something breaks, it's going to send an alert. Or if there's motion detected in the dark, it'll also send an alert. the file on the right, which is displayed, which is concatenated on the page, is a sound Python file, which we already went over. It obviously imports the required libraries. It has a function called detect sound where it establishes pin number 17 as the input pin, and it has a callback function where it has a callback function that it launches when sound is detected, and it waits till sound is detected. And we went over that already. So to add on to that, we have a motion Python file that we wrote that has a similar implementation, but it utilizes a completely different sensor. So for this one, as usual, we import the Raspberry Pi general purpose input-output library, and we also import the time module so that we can keep time. Like before, we define a function that helps us detect motion. This time we have pin number 23 as our GPIO input pin for the motion sensor. And this time we're going to put most of our program in a try except block because it's bound to fail at some point. So the first thing we do is stabilize the sensor, and we do that with the sleep, and that's where the time library comes in. And in a loop we put in we wait for the motion to be detected, and when it's detected, we finish up and we clean up, and that's the end of the program. But we still don't have something gluing these two things together. We don't have something to detect sound and motion together. So for that, we developed a very, very simple Python file that melds these two together called homesecurity.py. It's essentially just glue that puts these two Python files together. All it does is it imports both the functions from the sound module and the motion module, and it runs both those functions. Another potential implementation that we'll look at a little bit later is asynchronous running of the sound module, which allows the motion module to work a little bit better, but that's completely optional. I'll explain how that works in a little bit, but it takes a little bit more effort. But let's move on to the results.
Alright, so this is the program we're working with now, and as you can see, the main thing that we're doing here is we're asynchronously launching the sound detector, which means that it will run in the background as the motion is being detected. And one thing to note is that once the motion is detected, it has a sort of delay where it can't detect motion for a certain amount of time. So once it detects motion, it's done. The program quits. So let's try it out. The program is called homesecurity.py, and let's launch it. And so the first thing we're going to do is wait for the calibration to complete. It was quite quick this time, but it can take up to 1 minute. Let's try the sound detection and see if that works. Ah! Help! Alright, so it seems that the sound detection works. Let's try the motion now. As you can see, the motion has been detected as well, and the program is quit.
Alright. If we want to take this project one step further, we're going to need to know how to interface with other mediums. We can send data either globally or locally. If we want to go globally, we can use Ethernet through RJ45 and Wi-Fi. If we want to do a project that's in the household or more locally, Bluetooth will suffice.
So which internet protocols really facilitate this sort of communication both globally and locally? Well, the backbone of internet communication in general has been IPv4 for almost 2 or 3 decades now, and IPv6 is a newcoming technology that vows to replace IPv4 with its more secure handling of the internet. Two other backbones of the internet are obviously TCP and UDP packets, which carry all the information that we send up to the global network and back. And so the Raspberry Pi most effectively uses this to transfer data, to relay information, to make IoT as important and as effective as it can be. But how can this really help us improve our basic security system that exists now? Well, one of the potential solutions is adding another sensor, which may help us gauge more information from what we currently have. And this sensor is actually the ultrasonic sensor. And the ultrasonic sensor, if you don't know, measures the distance from where the motion happens to the location of the ultrasonic sensor. So it basically measures distance. And since distance is not an analog reading, we're going to have to do a lot more setup work for this, but I think it'll pay off since we can detect the location of the intruder and detect the presence of the intruder as well. And since we were talking about the internet and transferring data to better our IoT skills, we're going to be sending alerts through the internet to the phone, through email, to make sure our client or whoever installs this home security system knows that their house is being invaded or that the sound is present or anything like that.
All right, for this final Raspberry Pi project, we're introducing an ultrasonic sensor which measures how far away motion occurs. So for example, if I put my hand right here, it'll say about, I don't know, 5 centimeters or something like that. So we've got the ultrasonic sensor here, we've got our usual sound sensor, and we've got our little buddy, the motion sensor right here. So the motion sensor, keep it as it was in the last project. We're just going to connect it right to the Raspberry Pi. But now we need a rail to set up the ultrasonic and the sound sensor because we ran out of power pins on the Raspberry Pi. So this is quite a complex setup for the ultrasonic sensor. You're going to need 2 resistors, one of them about 500 ohms and one of them about 1,000 ohms. Double the first one, and it's going to be set up in this sort of configuration, and a detailed step-by-step guide is provided in the handout, so please follow that. It's quite hard to explain over video, but after you've done that, the sound sensor setup is quite easy actually. You plug it in wherever you want, and you're going to have the power pin be a male-to-male connector going from this to the positive rail on this. And then the rest of them just go right to the Raspberry Pi, just like we did the last time. This ensures that this power pin and this power pin go on the same power source on the Raspberry Pi. So let's get to the software part of this.
The software side of things is quite a bit simpler than the hardware side of things, fortunately. So as usual, we have the calling of the Python interpreter. We have the importing of the Raspberry Pi general purpose input output. We have the importing of the time module. These are all sort of standard things across all Raspberry Pi programs. We set the mode for the general purpose input output. And actually, I've left out a part of the setup, which sets the pin for the trigger and the echo. You'll have to figure out based on the instructions and the manual which pins those are. It is stated in the instructions, so if you pay attention, you'll be able to do it really quickly. In the detect distance function, we actually have some weird things. We first pass a current through the trigger, and that's the output pin. And we note the start time and the end time. And using these 2 times, we use the speed of sound to calibrate how much of a distance is between the start time and the end time. And so you'll notice the weird number 34,300. So that actually means that sound travels at the speed of 34,300 centimeters per second. We basically use that as a measurement to find out how much distance is in between the ultrasonic sensor and the perceived object, or the intruder in this case. So let's move on to the other 2 main files that we've modified. The first one is obviously the one that interfaces with the internet, and that one is an example of a Python sending an email over the internet. So this one, our imports are going to be very different because it's not a Raspberry Pi module. We're going to import SMTP-lib, and SMTP is actually an email protocol. We're going to import various other email protocols from email.mime, and we're going to define a function as we usually do. This one's called send email, and it takes a parameter called text. So for example, if the text is danger detected, it'll put that in the email in the subject line. So obviously we're going to define the sender and the receiver. In this case, the sender and the receiver are the same person. You can have the sender be a different person. It's all up to you. We have a lot of configuration using MIME multipart. That's something imported. We configure the body of the email with HTML. That's all just a layout. And so when you attach the message with MIME text and you send it over the internet, You just simply log in with the password and the account that you've inputted. You send the email and then you quit out. It's quite simple, really, and Python makes life quite easy for us to send an email using HTML and MIME. So let's take a look at the modifications we've made to the Motion program. There are actually no huge modifications except for we notice that there's an ultrasonic import at the top. We import all of the modules, all the methods from the ultrasonic file, which is obviously just the detect distance. And when we go down all the way to the if conditional statement, you see that after motion detected, it says the distance equals detect distance. So it actually detects the distance and takes the return value and stores it in distance, and then it sends the email with the motion detected at the number of centimeters away. So it actually attaches the distance to the email and it prints it out on screen. So those are the new additions to the motion.py file and the completely new email.py file as well.
Alright, so let's execute our final project, but before we do that, let's take a look at some of the changes we've made to our motion detector file. Here, instead of just saying danger motion detected and just leaving that as a string, we're going to detect how far away it is right here by using the ultrasonic function called detectDist2, and that's imported right there. And once you get that string, we just add that to the message and we print that out. And the new addition obviously is as well the email sending. So once we get this alert, we're going to get an email as well. So let's try it. Like always, we're just going to do /homesecurity.py, and that file has had no changes. So let's try it. The calibration is complete, so let's try the sound first. Alright, so as you can see, there's some sound detected. Let's try the motion. Remove this, and the motion's been detected 3 centimeters away. And as you can see, that's approximately 3 centimeters. And when you go over to the right here, you can see that we've gotten several emails. The first one is that there's been sound detected, and the second one is that motion was detected 3.17 centimeters away. And so our project was a success, and that's it.
As we have reinstated, IoT's possibilities are unlimited and allow for new opportunities in many areas. Instead of a binary analog input for most data sources such as the sound sensor and the motion sensor, a variable data source such as digital or discrete sensor would be of better use since it detects a range in motion or a range in sound. This also allows for small sounds or small movements, such as a rustling in leaves or a small animal moving through, to be ignored, providing more accurate data as well. With additional funds, better sensors can be acquired and these measures can be put into place quite easily. In general terms, the future of Pi lies in revolutionizing low-cost computing, as it is able to hold the power of an entire full-fledged computer at the size of a credit card with all the appropriate ports and software and other functionalities. It is also user-friendly, as it is easy for beginners to gain an interest in computers without being overwhelmed and exhausted. Pi will probably also try investing in more powerful hardware to achieve their goal more effectively.
So now that we've talked about IoT, its applications, what we can do with it quite simply with the Raspberry Pi, let's actually talk about what the future holds for IoT and its development in the industry. Well, obviously we've talked about how IoT has become so ingrained into our lives over the last 10 or 15 years, and that's simply going to continue. There's going to be more in-depth integration of smart devices into our daily lives, such as the Amazon Echo and the Google Home. There are many smart homes nowadays. That will become more and more common as time goes on. Cities and states, countries will become smart to save on valuable resources such as money, technological capability, all that sort of stuff. And one potential improvement that I see to happen is the advent of more secure measures, especially with cryptocurrency becoming very popular nowadays. More secure end-to-end bank transactions that are fueled by IoT innovations. and crypto security innovations as well. And before we finish off, a huge thank you to Rajesh, who helped us throughout this entire project. We visited Cisco headquarters with him, and we gained a huge insight into how IoT works and what sort of work goes into IoT as well. He taught us a lot about the Raspberry Pi and how to use it and the basics as well. So we owe a lot of this project to him, and we can't say thank you enough. Thank you for coming, and please let us know if you have any questions through our email address. Thank you.
We hope you enjoyed our quick Internet of Things workshop, and we would like to invite you over to join us at DYC for more programs just like this. We offer opportunities to grow in anything from leaderships to passions or any particular subject, as well as fruitful community service work. We look forward to seeing you again.
For specific questions about this workshop, please email us at designyourcareersprojects@gmail.com, or for more general questions, email us at info@designyourcareers.org. Thank you so much.
Thank you for watching. For details, visit www.designyourcareers.org or send an email to info@designyourcareers.org. Subscribe to our channel, Design Your Careers, and hit the bell icon so you'll never miss a video.